As you can observe, there are people laying tile. To determine how much tile they'll need to cover the space they want to cover, they must know the area of the tile they're using, and they must also know the area of the space they want to cover. Covering spaces with tiles relates to using another type of tile, and that's algebra tiles. Today, we're going to use those same concepts to explore polynomials. We're going to use algebra tiles. We're going to connect the algebra tiles and cover spaces to be able to generate pictures of given polynomials. Now let's take a look at an everyday situation where tiles are used. In your home, if you wanted to cover your bathroom or your kitchen floor, for example, with tiles, you would need to know the exact area of the floor you needed to cover. You would also need to know the exact area of the tile you would be using. Now let's take a look at how tiles relate to polynomials. We'll use the blue square tile to represent x squared, the green rectangle to represent x, the yellow rectangle or the yellow square to represent our positive 1 unit. The red large square will represent our negative x squared. Our negative x will be represented by the red rectangle, and a small red square will represent our negative 1. To show the polynomial or to demonstrate a polynomial, which is one term or the sum or difference of two or more terms, we'll use the terms of 7x, 2x squared, and 8 as a demonstration. To show a positive 7x, we of course use the green color, since that's what we designated as positive x, and 7x is simply 7 rectangular pieces. 2x squared, a positive 2x squared, will be blue, and there'll simply be 2 of the blue squares. A positive 8 is a combination of 8 of the yellow squares, since we designated yellow to be positive. As a further explanation or demonstration of the use of tiles, since a polynomial is one term or the sum or difference of 2 or more terms, we can use 4x plus 5, representing 4x with 4 rectangular squares and the 5 yellow squares, and a picture of 3x squared plus 2x plus 4 includes 3 blue squares, 2 green rectangular squares, and 4 yellow squares. Now, let's talk about the degree of a term. The degree of a term is the exponent of the variable. For instance, in the term 7x, the degree of that term is 1. 7x is represented by 7 individual rectangular pieces. 2x squared, the degree of that polynomial is 2. And it's represented by 2 blue square pieces. The degree of the term 8 is 0, since x to the 0 power is equal to 1, and 1 times 8 would give us the 8 yellow square pieces. Now, let's talk about the degree of a polynomial. The degree of a polynomial is the degree of the term with the highest exponent. Out of the terms 7x, 2x squared, and 8, the term with the largest exponent is 2x squared. Therefore, that would be considered the term of highest degree in this picture. Now, let's move on and talk about the monomial. A monomial is what we've been experiencing thus far, a one-term phrase, such as 7x, 2x squared, and 8. A binomial is a phrase, math phrase, with 2 terms in it, such as 4x plus 5, represented by 4 rectangular green pieces and 5 yellow square pieces. A trinomial has 3 terms, such as 3x squared plus 2x plus 4, represented by the 3 blue square pieces, the 2 green rectangular pieces, and the 4 yellow square pieces. Now, the arrangement of polynomials, trinomials, binomials, are normally done in what's called the standard form. The standard form is the form in which the terms decrease in degree from left to right, and no terms have the same degree. Let's take the trinomial 2x plus 4 plus 3x squared. The standard form of that polynomial is 3x squared plus 2x plus 4, represented by the 3 blue square pieces, the 2 green rectangular pieces, and the 4 yellow square pieces. Now, since we know how to recognize the tiles we'll be using in our polynomial representation, let's take a look at the use of tiles for the multiplication of polynomials. You've got 5 times 2, resulting in the partial product of 10. 5 times 1, giving you 5 with the 0 in the 1's place, giving you a partial product of 50. 1 times 2, giving you 2 with the 0, holding that place. And 1 times 1 gives you 1 with 2 zeros as placeholders. When you add up all of these partial products, you'll end up with 180. That's one easy way of doing that. Now, if you'll take a look at multiplying binomials the same way, from the way we explain the use of our tiles, on the horizontal part of the picture, you have x, positive x, plus 2. On the vertical part of the picture, we're multiplying that times positive x plus 5. And if you'll notice, the squares and rectangles are completely covering the area that's made by the factors we'll multiply. Our product generates another complete rectangle. Positive x times positive x is represented by, sure, x squared. Positive x times 1 is positive x. Positive x times 1 again is positive x. The second one is 1 times x gives us x, and 1 times 1 is 1. 1 times 1 is 1. We finish this until all of the 1's have been multiplied times the 3 terms in the horizontal factor, giving us the answer of x squared plus 1, 2, 3, 4, 5, 6, 7x plus 2, 4, 6, 8, 10. X squared plus 7x plus 10 is the product of x plus 2 times x plus 5. Our partial products again are x squared and 2x and x plus 2, x plus 2, x plus 2, x plus 2, and x plus 2. Another concept that's to be considered when you're using algebra tiles is the idea of zero pairs. Zero pairs are exact opposites. It's very important that you understand what zero pairs are, because they're used when you use algebra tiles to solve equations. Zero pairs are called just that because exact opposites always zero each other out. Exact opposites such as positive 10 and negative 10 put together result in 0. Now, since we've talked about how to use the algebra tiles in binomial multiplication, let's actually use them. If you'll notice in the picture, we have two binomial factors, x plus 2 and x plus 4. To find the product of those two factors, the binomial factors, two binomials which represent a product, we do just as we did before. Multiply each vertical term times each horizontal term. In the x plus 4, we first multiply with the x. In the x plus 2, we multiply times the x first. From the x plus 4, we multiply with the x times the 1, and then the x times the other one, just as we did before. Therefore, you've got x times x, giving you x squared. X times each one of these result in a positive x. 1 times x results in x, and 1 times each one results in 1s. This method is carried out until a complete rectangle is formed to fill the space that's generated by the horizontal and vertical factors represented by the tiles, giving us the result x squared, 1, 2, 3, 4, 5, 6 x, and those being positive because they're green, and plus 2, 4, 6, 8. Let's take a look at the use of another one. Multiplying the binomials x minus 3 times x plus 1. I know you know how to do this by now. You know that your answer is going to cover the complete space, just as the tiles would in your bathroom or kitchen that you want covered. Multiplying each term from the vertical factor represented by those tiles times each individual term in the horizontal factor, giving us x times x being represented by x squared, positive since it's blue. X times 1 would give us a positive x, and a negative 1 this time times a positive 1, resulting in a negative 1. If you'll notice, anytime you multiply two opposites, the result or the product is negative. That's very important. Anytime you multiply two opposites, the result is negative. Therefore, when we complete our rectangle, we end up with x squared positive, a negative 2x, because we've got 3 negative x's and 1 positive x. And in this idea, we get to see the use of zero pairs, since a positive x and a negative x will cancel each other out, leaving only 2 negative x's to be included in the product. And then 1, 2, 3 negative 1s equaling a negative 3. The product of x plus 1 times x minus 3 is x squared minus 2x minus 3. Now, let's take a look at a different concept involving polynomials, the difference of two squares. We'll use the concept of x minus 2 times x plus 2 to demonstrate the difference of two squares with our algebra tiles. If you'll notice, the difference of two squares is for all real numbers a and b. A squared minus b squared represents the difference of two squares. The factors that generate the difference of two squares are represented by a plus b times a minus b. Now, our a in this case is represented by x, our b is represented by 2, causing us to have the factors of x minus 2 times x plus 2. X times x, positive times a positive is a positive x squared. X times a negative 1 multiplying a positive times a negative results in a negative always. This time a negative x. Again, positive x times a negative 1 results in negative x. Positive 1 times a positive x gives us a positive x. Positive 1 times a negative 1 gives us negative 1. Again, multiplying opposites, a positive 1 times a negative 1 gives us a negative 1. Now, when we take a look at the square this time, that's made by the partial factors that resulted from our multiplication, we end up with x squared. And look, we have positive 2x and negative 2x. The idea of zero pairs appears here, with negative 2 and positive 2 becoming 0 and not appearing in our product. Of course, positive 2 and negative 2 are what's called exact opposites that zero each other out. That's why they're called zero pairs. The remainder of our product is negative 1, 2, 3, 4. Another outcome or product that results from multiplying binomials is shown by multiplying x minus 1 on the vertical and x minus 3 on the horizontal. X times x is positive x squared. Positive x multiplying a positive times a negative is a what? Negative x. Positive x times a negative 1 again, represented by negative x. Positive x times negative 1 again is a negative x. The remainder is shown by negative 1 being multiplied times a positive x. Again, multiplying a negative times a positive always results in a negative, this time negative x. But a negative times a negative, two of the same signs, a negative times a negative, just as when we multiply a positive times a positive, results in a positive. A negative times a negative results in a negative 1, a positive 1. A negative times a negative results in a positive 1. If you'll read the rectangular space we have recreated as our partial factors, we end up with x squared, 1, 2, 3, 4 negative x's, shown by negative 4x, and 1, 2, 3, positive 3. One last idea we want to explore using the concept of polynomials is the idea of the perfect square trinomial. Just as in the difference of two squares, our product is represented by a square instead of a rectangle. A perfect square trinomial is represented by binomial factors that are the same, such as x plus 3 times x plus 3, positive x plus 1, 2, 3 on the vertical, on the horizontal, and positive x times 1, 2, 3 on the vertical results in positive x times positive x squared. Positive x times each one gives us positive x's. Positive 1s times the x give us positive x's, and positive 1s times each one on the horizontal gives us 1s. And if we count up everything we have, we don't have any zero pairs represented here. Therefore, our product includes x squared, 1, 2, 3, 4, 5, 6x, plus 3, 6, 9. I hope you've enjoyed using the idea of wild tiles to deal with polynomials. Let's review what we've talked about. A polynomial we defined. The degree of a term we discussed. The degree of a polynomial we also defined. We looked within the polynomials and came up with a monomial definition, a binomial definition, and a trinomial definition. We also discussed the standard form of a polynomial. We talked about and saw the use of zero pairs. We talked about and saw the generation of binomial factors using the while tiles. And we also looked at a perfect square and defined a perfect square trinomial. Let's get ready for our reinforcement activities, and I hope you have just as much fun as I had dealing with while tiles.